Hello everyone, welcome to Journey with Data. So today's video is all about the importance of graphs or plots in data visualization. So as you all know that data is everywhere, and with the advent of new technologies we are generating more data. Now to get the most out of this, we should have a clear understanding of what the data conveys. So this is where the data scientists or data analysts serve the purpose. Given a raw data, they will process and generate a narrative out of this. Of course, this is a multi-step process, and one of the key steps is data visualization, because generating inferences manually from big data is not feasible. So I will be discussing some important plots and their usage in conjunction with machine learning in this video and in the upcoming series. And this video will cover box plots and how they participate in the decision making process. So let's get started. So here are some basic graphs that you should have an understanding of, and they are box plots, scatter plots, bar plots, pair plots, line plots, heat maps, and histograms. However, there are many more graphs that we'll learn in the upcoming journey, but this video is focused on box plots and how they are used in conjunction with machine learning, what's their purpose like. And I will be creating videos on each and every graphs eventually. So let's get started. So now let's see what is a box plot. A box plot is basically represented by a 5-number summary comprising of the minimum, Q1, the first quartile, median, Q3, the upper quartile, and the maximum. So all in all, the minimum, Q1, median, Q3, and maximum, these are the 5-number summary through which a box plot is represented. And as you can see here, the data is divided into 4 equal parts comprising of 25% each. So that's a basic box plot. And the difference from Q3 to Q1, which is Q3 minus Q1, is known as the interquartile range. So in simpler terms, interquartile range is a measure of spread of the 50% of your values. So that's a 50%, 25 plus 25. So that's your 50%, and that's the interquartile range. It's also a measure of spread of the 50% of your values. Now, what is the usage of a box plot, which is the main intent for this video? A box plot is basically used, as I've also written it here, it is used to show distribution of numeric values. They're also used to compare between multiple groups. They're used to analyze skewness, variance, and outliers. So we will be discussing all these things mathematically. So, you will be able to get these things very clearly. Let's try to see these things mathematically. In the first cell, I am importing all the necessary libraries, and in the second cell, I am reading the data set, which is a car MPG data set here. Now let's describe this, and for the sake of convenience, I'm just transposing it. Now, as you can see that the output, let's see what this data set contains. So this data set has the following attributes: units, price, weight, and product type, or the P type. And this describe function represents the count, mean, standard deviation, minimum, 25%, and so on. So if you closely observe, you may find that this 25% here, from minimum, 25, 50, 75, and maximum, these were nothing but the 5-number summaries through which a box plot was also represented. So you can also calculate if somebody asks you, or if you want to know what's the median for this. For example, if I ask you what is the median for the price attribute, so you can straight away look at the 50th percent, the middle value, which is nothing but the middle value. So the median for this price attribute is 148.5, and minimum, this minimum here is 68, and Q1 here would be 104.25. and Q3 would be 262, and the maximum would be this. So these are the numbers through which we can construct our box plot very easily. So in this example, I'll tell you how to identify skewness manually, or how to check the distribution type manually. Now I've chosen the weight attribute for this example. In this cell, I'm just calculating the median using numpy.median for the weight attribute, and similarly I'll calculate mean using numpy.mean, and then I'm taking a difference between mean and median. If you were to visualize this manually, you can see that, let me print this. Let me print median as well, so that you can just tally it through this through the statistic summary as well. Let me print it. Now you can see here median is 2803.5 and the difference is 166.92. So when there is a significant difference between median and mean, you can expect long tails in the distribution. That is one point to note. So here there is a significant difference between median and mean, which is near about 167 units. So I can expect tails in the distribution. I cannot expect my distribution to be a normal distribution. Now let me take you back to the statistic summary here, which was generated using the describe function. Now this, if you can see here, 2803.5, the value at the 50th percent, it is nothing but the median, and this is what we got using the numpy.median function as well. So that confirms the value of median. Let's now understand this concept in detail. As you can see in this diagram, that a normal distribution is shown and then a box plot is also drawn to represent it, this box plot. Now this area, the area that's highlighted in green, these areas, the area under this part, these are the tails of the distribution. Now the difference from, if I take a difference between, and this is the minimum part of the box plot, and this is the first quartile Q1, this is Q3, and this is maximum part. Now if I just take a difference between Q1 and minimum, which is Q1 minus minimum, this difference, this should give me the left tail, this part. This should give me the left tail, and if I similarly take a difference between Q3 and maximum, this should give me the right tail of the distribution. Now if, for example, if the left tail extends way beyond than the right tail, then you can say that the distribution is left skewed. Similarly, if the right tail extends way beyond than the left tail, then the distribution is said to be right skewed. So I'll demonstrate this through an example. What I'll do is I'll just take a difference between I'll just take a difference of Q1 minus minimum and Q3 minus maximum, and then we'll compare if left tail is longer than the right tail or whatsoever the case is. So let's see. So now let's calculate the left tail and right tails of the distribution, and this time I'm using the weight attribute. Now the right tail for the distribution is nothing but this value, difference between this value, which is Q3 and maximum. And similarly, the left tail would be this value. The left tail would be this value, which is Q1 minus minimum. And that's what I've done here. I've just subtracted both of them. And let's see what the output is. So the right tail is this and the left tail is this. Now on seeing the results, we can say that this distribution, because here the right tail is not similar to the left tail, the right tail is quite elongated as compared to the left tail. So what we can say is that this distribution is a right skewed or a positively skewed distribution. So let's confirm this through our plot as well. Let's move ahead. I'm simply using the Seaborn library and importing the necessary libraries like Seaborn and Matplotlib, and just plotting a box plot, sns.boxplot for the weight attribute, and then I am using the color for median and mean as well. Now if I plot this if I plot this for the weight attribute, you can see this, the right tail extends more than the left tail. So this confirms that this is not a normal distribution. And you can also confirm this using a box plot as well. See this blue line and the red line here were nothing but the blue line was median and the red line was mean. So you can say that this distribution is a positively skewed or a right skewed distribution. So as I told you that this red line represented mean and this blue line represented median. So in a positively skewed distribution, mean is greater than the median. And it is quite evident from this picture. Now let's go to this diagram, and I've taken this picture from the internet just for the representational purposes. So this is how a symmetrical distribution looks like, where mean, median and mode are same. And in a positively skewed distribution, mean is greater than median. And similarly, in a negatively skewed distribution, median is greater than mean, and so on. So this is how a negative or a positive skewed and a symmetrical distribution looks like. Now let's see how do these things fit into a box plot. Because up till now we were discussing the skewness, you were calculating and we were checking for skewness using only the number point summary. Now let's see these things from a visualization purpose as well. See, this is how a symmetric distribution looks like, and the data, if you can see, the median is at the center of the box plot. And in a skewed distribution, the median will be on the either side of the distribution. For example, here this is a right skewed distribution because the right part is quite elongated as compared to the left part, and median is also not at the center. So this is how a skewed distribution looks like in terms of a box plot. And that was the first usage of a box plot, to check for skewness. So let's see how to compare data from different groups using a box plot. And in this example, I've taken data from different groups two groups consisting of the survived and the died infants, and it is represented in terms of their birth weights. Now, whenever you are comparing different box plots, make sure you compare their medians, you compare their interquartile ranges, you check for potential outliers as well. And in this example, the median for the survived infants is greater than the median for the died infants. And there are no potential outliers, and this survived class has a wide range of values as compared to the infants who died. So I can establish a relationship in terms of the null hypothesis, and then I can extend this test beyond, and I can draw a conclusion that nearly 75% of the survivors were heavier than the median birth weight of those who died, meaning infants with heavy birth weights are more likely to survive. So that's just an observation that we can draw from this box plot. So you can also extend this test to go beyond the median, and you can also confirm your observations. You can also confirm the validity of your hypothesis tests, meaning you can carry out a 2-sample t-test. You can also carry out an ANOVA if you want to assess the equality of 3 or more groups. You can carry out a 2-sample t-test if you want to assess the equality of 2 group means. So these are the tests that you can use in conjunction with your observation to confirm the validity of your observations as well. So this was all about the box plots. I hope that this must have made some sense, and this must have given you clarity that box plots are basically used to check for the type of the distributions. If it's a normal, if it's a skewed distribution, we can also use a box plot to compare data from different groups as well. So I hope that this must have given you a quite amount of knowledge, and please do like, share and subscribe to the channel for more videos on data science, machine learning and Python as well. Yeah, thank you so much.